Hello and welcome to Kognito Key. Today, we're going to pull back the curtain on something we use every single second, the internet. We're going to explore the incredible, invisible highways that carry our data across the entire planet in, well, the blink of an eye.
I mean, have you ever really thought about it? You hit send on an email, and boom, almost instantly it arrives on the other side of the world. How on earth does that actually happen? It's not magic, I promise. It's actually a super brilliant system for routing all that data.
So let's think about how you'd solve this. The first idea that might pop into your head is, well, why not just connect every single device with its own wire? A direct point-to-point connection. But just try to imagine that for a second. Billions of devices. That would mean a literally impossible number of cables. It would cost a fortune and be the biggest mess you've ever seen. And on top of that, most of those connections would just be sitting there doing nothing. So yeah, clearly we needed a much, much smarter way. And that smarter way began with the very first major solution, which is called circuit switching. Now, to really get your head around this, I want you to picture those old-school telephone operators you see in the movies, the ones physically plugging in wires to connect a call. So here's the basic idea. Before you can send even a single bit of information, the network has to create a dedicated, totally unbroken physical path, all the way from you to the person you're contacting. It's kind of like reserving an entire highway lane just for your car. And once you're done, that connection is cut and the lane opens up again. Yeah, it's pretty much exactly like a traditional phone call. For the whole time you're talking, that line is exclusively yours. No one else can use it. Your entire conversation just flows down that one single, unbroken path from start to finish. So what's the good part? Well, it's super reliable. You've got that dedicated path, so your speed is always consistently high. But, and this is a big but, the major disadvantage is how inefficient it is. Think about it. That whole path is blocked just for you, even when there are pauses in the conversation and nobody is talking. That wastes a ton of bandwidth. It's a really wasteful system if that line isn't being used every single second. Okay, so to get around that massive inefficiency problem, engineers came up with a totally different approach, and this one is called message switching. Now, with message switching, there's no dedicated path. Not at all. Instead, your entire message, let's say a whole email, gets sent to the first switch or node in the network. That switch then stores the complete message, just holds onto it, waits for the next link in the chain to be free, and then it forwards it along. This is exactly why they call it the store and forward technique. A really great way to picture this is the good old postal service, right? You don't have a special dedicated road from your house straight to your friend's house. Of course not. Instead, your letter goes to one post office, they hold it for a bit, then send it to the next one, and it just keeps hopping from one point to the next until it finally gets where it's going. So the big plus here is that the network links aren't blocked anymore. This cuts down on traffic and lets way more people share the network at the same time. But the downside is pretty big. Every single one of those switches needs enough storage space to hold the entire message. And messages can be huge. And as you can imagine, this whole process of storing, waiting, then forwarding it every single stop, well, it makes the whole thing much, much slower. And that slowness, that was a real deal breaker. We needed something that was both efficient and fast. And that's when the real game changer arrived. Enter packet switching, the true engine of the internet we know and love today. Okay, this is where it gets really clever. Instead of sending one giant message all at once, the idea is to chop it up into thousands of tiny, little, manageable pieces. We call these packets. Each one of these little packets is then sent out into the network on its own little journey, and they all get put back together in the right order, of course, at the very end. Honestly, the best analogy for this is mailing a book, but page by page. Imagine you put each page into its own small, numbered envelope, then you just drop them all in the mail. Now, some of those envelopes might take the main highway, others might take a scenic side road. Their routes could be totally different. But because every single one is numbered, your friend can easily reassemble the book perfectly once they all arrive. Now, even within pocket switching, there are a couple of ways this can happen. First, there's the datagram approach. Here, you can think of every single packet as a solo driver with its own GPS, finding the absolute best route available at that exact moment. Super flexible. The other way is called the virtual circuit approach. In this case, the first packet is kind of like a scout. It goes ahead and finds a good path, and then all the other packets from that same message just follow right behind it, like a train on a single track. So what's the result of all this? Well, you get an incredibly efficient use of bandwidth because the network is being shared by countless little packets all at once, and you don't need those huge storage drives on the switches anymore. The main trade-off, though? Because packets can take all these different routes, some might show up a little later than others, which can create tiny delays. And that's why it's not always perfect for things like a live video call, where even a tiny split-second lag can be really, really noticeable. All right, let's do a quick recap and put all three of these ideas side by side. When you see them all together, it becomes crystal clear why one of them completely took over and now runs our world. So here's the final breakdown. You've got circuit switching, which gives you that dedicated path, but its efficiency is really low because that path is completely blocked off. Then there's message switching, which solves that blocking problem, but having to store the whole message at every stop makes it so slow. And finally, you have packet switching. No dedicated path, tiny little data packets, and just incredibly high efficiency because everyone can share the network highways all at the same time. So if there's one thing to take away, it's this. It's that beautiful combination of flexibility and super high efficiency in packet switching that allowed the internet to grow from just a small project into the massive global network that connects all of us today. Seriously, every single time you stream a movie or send an email, you are using this absolutely incredible system. But all of this leads to a really fascinating question for the future, doesn't it? I mean, with the absolute explosion of data from things like AI, 4K streaming, the Internet of Things, our demand for instant perfect connections is just getting bigger and bigger. So the question is, how will these fundamental ideas need to change and evolve to handle the next generation of the Internet? Thank you so much for watching Kognito Key. If you found this explainer useful, we would love it if you hit that subscribe button. And of course, don't forget to like and share this explainer with anyone who might be curious about how our digital world really works. We'll see you in the next one.